Hello and welcome. This is Bijan Hoshiar. For communication to be successful, it requires source or signal transmitter, destination or signal receiver, medium for data to travel on from source to destination, and protocols. Protocols are responsible for message encoding, message encapsulation and formatting, message size, message timing, and message delivery options. Message encoding means that the sending host is responsible to convert the message into bits represented by magnetic waves for wireless medium, light waves for fiber optic medium, and electrical impulses for copper medium. Encapsulation starts on sender host at transport layer and continues on network and data link layers as well. In here, an example of that encapsulation performed at network layer by IPv6 is shown. IPv6 protocol is going to add different fields to the data to create a packet. Those fields include version, traffic class, flow control, next header, hop limit, source and destination IPv6 addresses. Frames have size restrictions. Source host will break a long message in two pieces in order to meet minimum and maximum size requirements. Message timing parameters are access method, flow control, and response timeout. Access control means checking the availability of the medium by the sender host. Flow control means to manage the rate of data transmission in a way that the receiver can handle those packets. Response timeout means how long to wait for a response to come back from the destination and what action to take if a response timeout occurs. Message delivery options are unicast, broadcast, and multicast. Unicast is one-to-one communication. Broadcast is one-to-all communication. Multicast communication is communicating with a selected few within a group. Protocol suite is a group of interrelated protocols such as TCP/IP implemented by networking hosts. There are two networking communication models. They are OSI and TCP/IP. OSI is a 7-layer communication model. TCP/IP is a 4-layer. The layers of OSI and TCP/IP map to each other. Application layer of TCP/IP performs the same functions as application, presentation, and session layers of OSI. Transport layer of TCP/IP performs the same function as transport layer of OSI. Internet layer of TCP/IP performs the same functions as network layer of OSI. Network access layer of TCP/IP performs functions of data link and physical layers of OSI. Each layer of these communication models provides service to its upper layer. Each layer has a protocol data unit for communication with its peer layer on the other end of the communication line. Data is the protocol data unit for application, presentation, and session layers. Segment is protocol data unit for transport layer. Packet is protocol data unit for network layer. Frame is a protocol data unit for data link layer, and bit is a protocol data unit for physical layer. Each layer has some protocols residing in it. For example, HTTP, FTP, DNS, and SMTP are some of the protocols residing in the application layer. TCP and UDP reside in transport layer. IP is a protocol residing in network layer, and media access control or MAC is a protocol residing in data link layer. Encapsulation occurs on sender side by adding header and trailers. The encapsulation occurs on the receiver side. It is the reverse process of encapsulation. On the sender side, upper layer applications encode application data. Data gets to transport layer. It will be chopped into pieces called segments. Each segment will be encapsulated by source and destination port addresses. Each segment will be sent down to network layer. Network layer encapsulates each segment received from transport layer into a packet by adding source and destination IP addresses to it. Each packet will be sent down to data link layer, and data link layer is going to encapsulate it into a frame by adding source and destination MAC addresses to it. Each frame will be sent down to physical layer to be converted into a series of binary bits to be put on the transmission line to go from source to destination. PCBON and FTP server are in the same local area network. PCBON wants to communicate with FTP server. PCBON needs source and destination IPv4 addresses and source and destination MAC addresses. PCBON knows its own IPv4 address. We are providing the IP address of the FTP server. For example, we are pinging that server. Therefore, PCBON is capable of completing the packet and including source and destination IPv4 addresses in that packet and send the packet to data link layer to create a frame by adding source and destination MAC addresses. PCBON knows its own MAC address, therefore it will include that under the field called source MAC address. Now PCBON needs the destination device's MAC address. PCBON first will check its ARP cache table. If that MAC address is already cached, it will use it and complete the frame and send it to physical layer. If it is not cached, PCBON is going to issue an ARP request. In that request, PCBON will ask a device with the matching IPv4 address to provide its MAC address in order for PCBON to start communication with that device. Since FTP server is in the same local area network as PCBON, it will reply to that ARP request by providing its MAC address to PCBON. PCBON is going to cache that MAC address in its ARP cache table and then include it in the field called destination MAC address in the frame and complete the frame and after that we'll send the frame to physical layer to prepare that frame and put it on the transmission line to go from source to destination. PCBON wants to communicate with a host that is located in a remote network. The process of adding source and destination IPv4 addresses is the same as the way it happened for local host communication. The packet gets to the data link layer. PCBON knows its own MAC address. It will add it as the source MAC address. It is looking for the destination device MAC address. It will check its ARP cache table. If it is not there, it will issue an ARP. Nobody in that local area network is going to be able to reply back because they don't have the matching IPv4 address. Router will take a look at that ARP request, realize that the destination device is in a different network than PCBON. Therefore, it will return the MAC address of the default gateway of the network that PCBON is located in as the destination MAC address. PC1 will use that as the destination MAC address in the frame, completes the frame, send it to the physical layer to prepare it and put it on transmission line. Eventually router gets that. Router is going to de-encapsulate it, change the source and destination MAC addresses and forward it to the next router. The next router will do that, de-encapsulate and encapsulate it again with a different source and destination MAC addresses. This process happens until the packet gets to the destination device. Therefore, we can conclude that layer 2 addresses are going to be changed as a packet is traveling over a layer 3 device such as a router, but IP addresses will stay the same from source to destination. Thank you for watching. If you liked the video and you found it informative, please don't forget to recommend it to others who may be interested. Thank you.